Okay, so good morning everyone. This is I think last week's. So would like to continue this the lecture, and for a quiz for chapter 12 and 13. Please wait for a moment. Okay, I'm just finishing some parts. Maybe this week I can upload, attach the link in the Moodle, and you can try to work on the quiz. Okay, so first here, after we get the linear approximations, another I think interesting point of view is we call this is differentials. Which we are going to take some partial derivatives elements and make it into some sort of equations. So if we take the equation of the plane in our partial derivative, or the tangent plane, as we know, we can write like this, right? Now visually, if we want to look into the graph for y and x, we can simply look at this as our differential, right? When we take difference in the when we add the delta x, then we have a significant delta y that is changing, right? Now if we want to see in more clear, so we have this tangent line here, right? Okay, so if we want to take the tangent plane, then perhaps this is the best way to elaborate the issue. So you can see that when we change our variable, which is x and y, so we have a delta x and delta y. So basically, what the tangent plane will be is z minus the point when we put the AB for the function. And the function itself is our z, okay? And then this is practically the same as our tangent plane equation. So this is for the first tangent line, the T1, T2, right? And then you will see that it will change some delta, right? But if we want to make it more clear in terms of differential, which means that we are only focusing on a small segment, we can denote this as dz. So this is actually the same thing, okay? So the same thing, just different, a little bit different in how we write, okay? So we can write from here, and then as small and as z minus z0 getting smaller and smaller. Okay, so this is getting a delta, and then makes more smaller and make a small segments, and we say this is a dz, right? Say this is dz, and we can say this is partial x of that point xy dx plus partial y of that point dy. Okay. So this is, we'll just get into, this is delta x, delta y, this is delta z. Okay. So as the delta getting smaller, we can rewrite the equation with terms d, right? And then we can maybe write in more a simple way like this. Remember, when you have partial, you need to use the Leibniz notations to denote that this is partially derivable. Okay. Okay, and then if you remember what we have in the linear approximation, is dz or let me just write directly, f xy, we can approximate f ab plus dz. Okay. So basically we say that this is z, this is c0 at the point, right? And this is the dz. And dz, we can simply write dz in terms of partial. So this is just a slight changes when we write. And basically they are the same thing. So we can write this form. Okay. We call this is differentials, which perhaps you are going to elaborate these differentials, I think, in another course. I think in engineering of math, you can have more elaborations on within this differentials. Let me make it smaller. This is not really important for this course, but this is just a review from calculus 1. This one is the one that we are talking. Okay, that's the first session for today. The next part is I would like to go to chain rule. So my goal today is perhaps chain rule, and we call the gradient factor. Okay, the gradient factor. Okay, hopefully we can finish that part, and then maybe have some review if we have time. Okay, let's move to the chain rule. Okay, you can just take some picture, because this is just another writing on the tangent plane equations, and we can make it into what we call differentials. So nothing really new. Okay, let me move to here. Okay, so we start by, maybe before we take this chain rule, let me just explain a little bit on what we are going to have. So chain rule in the partials. Okay. Remember that in parametric equations, we already look how we take the dy over dt, we write as dy over dx, and then multiply with dx over dt. Okay, this is basically chain rule, and we define that dy over dx. Basically dy over dt divided by dx over dt, right? So we take the parameter t, right, to help out the definitions. So basically, in our way for partial derivative, so if we take the z as a function of two variable xy, and if we can define this x and y in terms of one variable, okay. So for example, if x is, let's say f is, let me just write x t like that, which means that the variable will be t, and y we can write in terms of y of t. Okay. So we can rewrite z in terms of x t and y t. So the implication that if we write like this, then z itself, okay, can be expressed as a function of t, right? A single variable t. So which means that if we have this kind of structure, then we can make the chain rule out of this z. Okay, so you can see from this chain rule case 1 here. So suppose that z is a function of two variables x and y, and then we can define x as g of t, y is h of t. Then we can define this partial derivative as a chain rule. So dz dt is equal dou f dou x, which is we can say partial x dx dt, and then partial y dy dt. Okay. So whenever we can relate z and x and y, and x and y they are related to the parameter t, then we can say we can make out the chain rule from out of it. Okay. Let me write here example on the right side. So let's say we have z x squared y minus y squared, and we have x is sine t and y is e with power of t. And then the question is find dz dt at t equals 0. So we can start by taking this dz over dt equal the partial, right? And then the x dt, okay? And then plus partial y and then the y dt. Okay. So basically we can move one by one, okay, from one expression to another expression. So maybe we can start from the partial, or we can start from the parametric derivatives. Each way, at the end, you need to multiply all together and put into the equations. Okay. So maybe we can start from the partial. So partial x means that we are going to derive with respect to x, and then taking y as a constant. Okay. So x squared y becomes 2xy, and y squared is constant, so 0. Okay. And dx dt is derivative of the function x equals sine t, right? So this will be cosine t. Okay. And then plus partial y. So we are derivative of we are going to differentiate z in terms of y, taking x as a constant. So x squared constant, so we derive y, so become just x squared, and then y will be negative 2y. Y squared will be negative 2y. And then y equal e with power of t, derivative the same, right? So we can just write e with power of t. Okay, and then we can just input the t equals 0. So dz dt at t equals 0. Okay, so we can input t equals 0. So first, perhaps we start from xy. If you want to make it into or maybe before we input this, maybe we can transform all the variables into one single variable t to help write the formula. But I think if you can just input one by one, and then I think it will be the same thing. But let me just write the x is sine t, right? 2 sine t, and then e with power of t cosine t plus, okay, let me, I think I need to make it a little bit down here, okay. And then plus sine squared t minus 2 t. Okay, I think we can take t equals 0. Okay, so when at t equals 0, dz dt is equal, so this will be 0, right, because of sine 0, and this will be 0, this will be -2, this will be 1, right? So we can finally just write this as -2. So you can think this as a parametric case. Okay, but I think it's best to look the partial derivative in more general way, not only just related to parametric. So for example, in another case, we might have this where z is function of two variables, but x and y is also function of two variables. Okay. So if you look here, it seems that we have partial and another partial. Okay. So for example, the first one is dou z dou s. Okay. So partial z, right, with respect to s, and then partial x and then partial s. But we write this. There's a pattern, okay, to help you out. Okay, if you look at the formula, look that because we have s and t in both x and y, and z are related to x and y, so we are actually writing z in terms of st now. So the key, we have these two components, right? Z, dz, dou z dou s, and dou z dou d. Okay, so it's not d because this is now partial. Okay, now all the terms we are going to write down a chain rule that resulting dou z dou s. So first, writing as usual, partial x like dou z dou x. And then the other one is dou z dou y. And both of this, we need to multiply and write the result need to be the same as this one. Okay. So look at here, you have dou z dou x. It needs to be multiplied with dou x dou s because we want to make dou z dou s as the left one. Okay. This is also the same. Dou z dou y and then dou y dou s, and then need to make dou z dou x as in the left one. And the same thing with the dou z dou t. Okay. Okay, if you still have some confusion about this, there is another way to look in more general. So if you have like many partials, 2 variables, 3 variables, 4 variables, it doesn't matter. So for example, if you have w is f x1 t, x2 t, x3 t, and we have more and more, we can write this in terms of, so if this is just one single variable t, we can write like this. And what we need is basically a tree diagram. Okay, so tree. Okay, for example, we have z. Okay, like the first case, like we did before. So let's say we have this. So we have z. There is function of 2 variables x and y, but x and y both are function of 1 variable t. Okay. So to help out, let's design the diagram. Okay. So first is z. This is the we call it the source. Okay. Z has two variables, right? X, Y. Okay. But both x and y is only having one variable. Okay. Like that. Okay. Whenever you move from the source and get down, okay. So for example, we move z to x. So we are going to take z with derivative. So dou z dou x. And we write with Leibniz whenever you see any branch. Okay. So whenever it hits branches, you will get partials, right? Because it's have more than one variable. But if it's only one variable like this, then the notations usually we just write dx dt. And this is dou z dou y dy dt. Okay. So this is what we call the tree diagram. So dou z dou t is equal and plus okay. So at the end we plus this with this. Okay. And now what's happened if we have more than, so still it's not getting into this one single line like this. Maybe it has branch. What will happen? So let me write on maybe here. Okay. We'll write this in this part and maybe anything up there. Let's say we are going to take z. Z is a function of, let's say x is having two variables like that, just like case 2. Okay, this one. Okay. So start with z in the top, and then it's branched into two, x, y, right? And then x and y, they both branches again into two variables, as t. This is also as t, right? Okay, now we have two variables at the bottom, right? So instead, just like one here that we just have dz dt, now we have dz ds and dz dt. But how is the component? We are going to make a path from here, 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 and here. Okay. So we take this one here, dou z dou x. This is dou z dou y. This is dou x dou s. This is dou x dou t. Dou y dou s. Dou y dou t. So we have two expressions for z. So we will write on the left here. Okay. So two expressions. For example, first one is dou z dou s. Let me mark the dou z dou s is this one with green. Okay. And this one here, right? Then we can write first is dou z dou x dou s, okay? And then plus dou z dou y dou s. Okay. That's the first one. And the second one, let me write in yellow. Yellow is here. Yeah, I hope it's not too messy. And the other one is that one. Okay. So dou z dou t, dou z dou x dou t, plus dou z dou y dou t. Okay. And any branches, how many branches we have, we can have more and more and more. Okay? As long as you consistent doing this diagram, I think you will get what will the chain will be. So sometimes maybe some problems giving you some conditions, then you need to define first where is the variable, how much the variable, and what is the relation between all the functions. So as long as you can understand the relations, you can make a diagram. I think any chain rule is, I believe, it's solvable. Okay, you can solve that chain rule. Okay. Okay, now maybe perhaps the example. Okay. So let me. This is just what we have before. Okay. So if we have many variables, you can have a lot of possibility. But if you want to write, so you can write. But I don't think this is helpful. I think you can just get into the tree diagram, and whenever you see the relations, you can go to the tree diagram. Okay. Let me give you example. So example, if you have u is x to the power of 4, y plus y squared z cubed, x is r s e to the power of t, and then y is r s squared e to the power of negative t, and z is r squared s sine t. So you have, at least at the very bottom, you have three variable r, s, t. And z, or here we consider z as part of the branches. So the source is u, right? The source is u. Okay. So you have three variables x, y, z. So we can just draw the diagram. Okay. So it can be like really complicated, but as long as you define and relate all the functions, you can get into the chain rule. So first is u, and then get into x, and then y, and then z, right? But x, y, and z, they also relate to the r, s, t. So we'll just write r, s, t. So r, s, t, okay, r, s, t, r, s, t. Okay. Okay, so if we would like to determine, let's write the question, determine the value dou u dou s, okay, when r is 2, s is 1, and t is 0. So we just focus finding this du ds, or dou u dou s, which means that only s, right? Okay, so let's just focus on that. So taking the dou u dou s is equal, we go here on the right, dou x, and then here is dou x dou s, right? And we go here, dou u dou y, and then dou y dou s, here's the same. So we write dou u dou x dou s plus dou u dou y dou z dou s. Okay. And then slowly but sure, we are going to partially derive all the components. So dou u dou x, this will be taking the function u with respect to x. So it will be 4x cubed y, 4x cubed y, and y and z is constant. So we just stop here. And then dou x dou s, we are taking s as a variable. So we just have r e to the power of t. So I think the best way to describe our method here is, as long as we take it slowly and careful when you derive all the components, I believe it should be solvable. You can solve this one. So dou u dou y is x to the power of 4 plus 2yz cubed And then what else? The y double s is 2 rs e power of negative t. Okay. And then last one, it's z cubed. So z cubed becomes 3y squared z squared. Okay. And the other one is constant, is 0. And dou z dou s is r squared sine t. Okay. So the rest is computations, and be careful when doing that. Okay. So t is 0. Okay, t is 0. So when t is 0, so for x cubed y, okay. So I think we can, if you want to write like x, so when r is 2, s is 1, t is 0, x is, so one by one we can write down here. So 2, so it's just 2, y is 2, also 2, and z is 0. So every z will be 0. So this is 0, this is 0, this is 2 by 3, it's 8, 32, 64, right? 64. R, this is 2. Okay. So x to the power of 4 is 16. And 2rs, this will be 4, right? R is 2, so 4. Okay, so we have 16 by 4 is what? 64. 64. 128, 64 is 192, right? So 192. And this method, this diagram, is also helpful for developing other technique as well. Okay. For example, if you remember in calculus 1, you have the implicit differentiation. You could have this similar implicit differentiation in partial derivatives. The difference is we are going to have more variables. Okay, this is the conclusion for the implicit, but let me write conclusion down here, Okay. Let me explain first what it is. Okay, so this part, I think a typical chain rule question, and I hope you get the idea. Okay. Do you still have any confusion about this one? As long as you know the functions and what the relation between all the functions mentioned, right? Okay, so let's go to the implicit differentiation. So let me just review. Okay. In calculus 1, if we take, let's say we have this, okay, and then find, usually we are going to find dy dx, right? And this is our supposed to be a function. And in calculus 1, we use this direct method to derive all these elements completely, right? And how we treat y, because y is function of x. Okay? We set assumption in implicit differentiation in the calculus 1 that y is always function of x. Okay? This is our base assumptions. Okay? So when we take this and we're doing the implicit differentiation, it means that we are going to derive y. For example, y cubed becomes 3y squared. But we need to add dy dx at the end, right? So we add 3y squared dy dx like that. And then we add another y here, and we get 2y dy over dx, right? And then 5 is become just 5, and then dy dx. okay? And then we just treat x as usual, negative 2x, right? And then it's equal to 0. And basically what we did is we are going to take all the component dy over dx, and then we are going to write here, and this is basically the answer, 3y squared plus dy minus 5, right? Okay, so we've done implicit differentiation, okay, in calculus 1, single variable, okay. Okay, now, because we know the chain rule in using the diagram, the tree diagram, so we can just use the same thing to solve this, okay. So let me just give you an idea here. So first, we decide to make the function just as f, and then make this f into two variable x and y. But x is just single variable, so we just stop x up until there, but y is having another variable x. So we can say that we can partially derive this and partially derive this. And here is just normal single derivative, right? So from here, if you want to just make all the components coming together, so dou f dou x, okay, plus dou f dou y, multiply dy dx, right? The total component. So this is basically saying that this is dou f dou x, right? So if this is equal to 0, okay, from the functions that mentioned, then we could write dy dx from here is basically negative dou f dou x over dou f dou y, or we could say negative partial x over partial y, which is, if we take partially, we are getting negative 2x multiplied with negative, so this 2x, right? And then partial y is 3y squared plus 2y minus 5, which is the same thing. Okay, just some additional information that I didn't record the second half of the course. So I'll just review the implicit differentiation in calculus 2. So it's helpful if we are drawing our tree diagram like this. Okay, and then if you see more on the definition, so if we take the function of two variable xy equals 0, we define y is implicitly differentiable because y is a function of x, so we can rewrite this and makes this f of x equal to 0, and the capital F function is differentiable. We can write this. Okay. And of course, this is going to be equal to 0 because of our definition here. And we can write the tree diagram. And then we can say that in terms of dy dx, the one that we usually found in our implicit problem in calculus 1 is equal to negative partial x over partial y, like that. Okay. But in more practical way, we can also try to solve this one here. And we say that we define all the variables, okay, and we have relation between functions. For example, from this capital F, we have 3 variables, and from Z, we have 2 variables x, y. And depends on what terms that we need to find, we can rewrite them and makes them into our implicit function theorem like this. So we find dou z dou x is equal to this, and dou z dou y is equal to this. Okay. And similarly, if you think like in calculus 1, we could also take these functions, and for example, if we take partially derived with y, it means that we are going to treat x like a constant, y we treat as a usual variable, and z we could treat with a special treatment. For example, here y squared becomes 2y, and z squared becomes 2z, and then don't forget dou z dou y. Same thing with x. If we partially derive with x, we have this. Okay, and this is the same result with this first method. Okay, so this is the second perspective that we can use. Okay.
And the other sections that we discuss within the class is directional derivative, okay, which we define based on what we have in partial x and partial y, which defines the tangent, right? We define the tangent plane, and the tangent plane is basically tangent line of partial x as a slope and partial y as a slope, right? And basically what it says is if we are going to have some vectors, for example this u, and we have this t that is going to be tangential with this point P, okay, so we could write how to represent the rate of change of z, okay, in terms of this unit vector u, okay. So let's say we are going to write this, okay, the rate of change of z, okay, in terms of h, okay, and then we take the limit of h equaling to 0, which means that we are taking it into derivative definitions. Okay, so this is the directional derivative. So directional derivative, again, that is rate of change of z in the direction of the vector u. And then from here we can write simply just directional derivative is equal to partial x a partial y b, and a b is from the vector u. Or we could write this directional derivative in terms of gradient vector. So gradient vector is actually our vector that compose of partial x and partial y. Okay, so this is going to be the dot product of this gradient vector and then the unit vector u. So that is the directional derivative. Okay, so this is directional derivative, and then we could say that directional derivative has a maximum value when theta is equal to 0, because we could rewrite this dot product in terms of the cosine theta, and we see that the magnitude value of u is 1 because the unit vector, and then the cosine theta will be 1 maximum, right? So theta will be 0. So we could just write that the directional derivative maximum is magnitude value of the gradient vector itself.